In the last class, we had discussed ARM instruction set. In a way, we have developed an understanding of ARM instruction set architecture. Today, we shall look at other features of the ARM architecture, in particular exception processing and the other components, how they go into the core, and also the internal organizational details of the processor core. So, before going into the exception processing, let us have a quick review. Actually, we have discussed these modes earlier. So, what I am showing here is the exceptions and the modes in which the ARM processor is expected to be in when such an exception occur. The interesting feature is what you find, and we have discussed it earlier as well, that corresponding to exception there is a mode switch, that the mode in which processor works changes when an exception occurs. So, along with mode change, what else happens? The core saves CPSR, that is current status register, to the SPSR of the exception mode, that is saved registers. Then it saves PC to the link register of the exception mode, sets the CPSR of the exception mode, and then set PC to the address of the exception handler. In fact, all of these exceptions are associated with a vector, that is a memory address at which the exception handler is expected to be located. But it is strictly not always that way, because the vector table, which is a table of addresses where ARM core branches when exception occurs, may not have space, and really it does not have space to put in the complete service routine in that table itself. So, in the table you actually have a branch instruction. It can be explicitly a branch instruction, or it can be any other instruction which modifies PC. So, on execution of this instruction, actually the control gets switched to the interrupt handler. So, what we have shown here is example of a branch address, another is LDR, which is loading the PC. Now, in this case an offset is added to the PC. So, it can be a signed offset as well, added to the PC, and that value is loaded onto the PC. What does that mean? It means the instruction located at that address will be executed as part of the interrupt handler. Obviously, this would involve a memory access to get the address, and this will therefore increase the interrupt latency. Now, in this case, move PC immediate, this is also an immediate address which can be loaded onto the PC. This gives you an ability to get or locate the interrupt handler anywhere in the memory, because the immediate operand can be appropriately changed and loaded onto the PC to provide the address. In this case, it is always a relative address. Now, these exceptions have associated with them priorities. So, I have listed here the exceptions and their priorities, and you will find the reset exception has got the maximum priority. And what does these two columns indicate? They indicate the value of I bit and that of F bit, which are bits in the status register when such an exception occurs. What is the meaning of this? Say in reset exception, when it occurs, this I bit is set, F bit is set, which in effect means that first interrupt request as well as interrupt request both are getting disabled. Similarly, when you see that data abort interrupt occurs, in fact, in this case the I bit is set to 1, but F bit is not set. So, interrupt, that is normal interrupt request, that is disabled, but first interrupt request is not disabled. When FIQ occurs, you will find that your both I and F bit is disabled. That means, if I am servicing FIQ and if I do not explicitly enable F bit or I bit, another FIQ cannot be serviced. Now, you will find for all these interrupts, you will find that I bit is getting disabled. So, normal interrupts are getting disabled. So, inside these service routines of these interrupts, if we are not explicitly enabling this interrupt, that is general interrupt cannot be serviced, but FIQ can be serviced. So, obviously, FIQ you can realize has got much greater weightage associated. Okay. Now, here also another interesting thing you should note, the basic difference between exceptions and interrupt with reference to the architecture. Now, if you look at FIQ, IRQ, these two interrupts typically occur because of external devices. External devices means devices outside the CPU core, but may be resident on the same silicon area itself. Software interrupt instruction is an explicit instruction as part of your code. But if you look at other, say data abort, prefetch abort or undefined instructions, they can happen because of some kind of an exceptional condition during execution of your code. Okay. So, these are therefore not really interrupts, interrupts being explicitly generated to interrupt your current flow of execution. Okay. So, when we refer to interrupts explicitly, we shall be referring to FIQ, IRQ and software interrupts. Others are exceptions, and everything put together is actually exceptions. Interrupts are also exceptions. So, how do you design exception handlers? Typically, reset handler initializes the system. It sets up stack pointers, memory, external interrupt sources if it needs to initialize the peripherals before it enables IRQ or FIQ, because you would not like to have spurious interrupts before the external devices have been initialized. And the other interesting thing is that you have to initialize stack pointers, because until and unless you set up the stack, you cannot really do processing of the interrupts, because you might need to save the registers into the stack. And the reset handler code should be designed in such a way that no other exceptions are really occurring or gets triggered while execution of this code. Because if that occurs, that may not be correctly serviced, because you have not set up the vector tables, okay, you have not set up the stack pointers correctly. So, all these things are to be done by the reset handler. The data abort interrupt occurs when memory controller indicates that an invalid memory address has been accessed. That means, may not be an physical memory located at that address, and so when such a location is being accessed, there has to be an exception, because that is an error condition, an exception has to be handled differently. So, this data abort interrupt, okay, I should not say that as an interrupt, a data abort exception is an error condition, and so I need to have an exception handler as part of my operating system to take care of that. But during this period itself, an FIQ exception can occur, because it is not really disabling FIQ, because FIQ is an external device. So, it might require an immediate FIQ may be generated from an external device, and it might require an immediate service. So, FIQ occurs when an external peripheral generates what I call FIQ input signal. And now core disables both FIQ and IRQ interrupts. That is, when FIQ is being serviced, I cannot have another FIQ coming or another IRQ, that is, which is of a lower priority occurring and interrupting my service routine. IRQ occurs when an external device generates IRQ input signal. So, in that sense, the modality wise FIQ and IRQ are identical, but FIQ has got a higher priority and more weightage. And also I hope you remember that there are a large number of register copies which become available in FIQ mode. So, the interrupt latency, the software latency would be much less compared to that of IRQ. So, IRQ handler would be entered if neither an FIQ exception or data abort exception occurs, okay, because the FIQ and data abort are of higher priority, and reset is not normally expected to occur other than when the system is booting up, that is the initial conditions. On entry, IRQ exception is disabled and should remain disabled for the handler if not enabled by the handler. That means, if I am not entertaining nested interrupt processing, I shall not do what? Enable IRQ inside IRQ handler. Okay. If I am not enabling nested interrupt handling, there may be increased interrupt latency. The prefetch abort occurs when an attempt to fetch an instruction results in a memory fault. In fact, it is very similar to data abort. Data abort occurs when you are executing an instruction, trying to get a data or write the data. Prefetch abort occurs when you are trying to get the instruction, the opcode. And in the same case, FIQ exception can be serviced even when the prefetch abort occurs. Undefined instruction occurs when an instruction that is a opcode which has been fetched and it is being attempted a decoding, and it is found that is not in the arm or thumb instruction. In fact, when it is not even an instruction of any of the co-processors which may exist on the core. And the interesting feature is the software interrupt as well as undefined instruction, they have the same priority level attached to them. And that is obvious because both these exceptions cannot occur simultaneously. And what happens and how we process software interrupt instruction, we have discussed in the last class itself. So, how do you return from exception handler? It can be using any instruction for that matter which will restore your PC to the corrected value of the link register. And what is important is that the exception handler must prevent corruption of the link register value which gets loaded when mode switch takes place. This is very, very important. And the other important thing is that the CPSR, okay, the current CPSR will be restored from saved program status register, okay. So, that CPSR gets restored from the saved program status register. And there is a subtle interesting point here. What I have written is that I am moving the correct value of link register R14 into PC. It is not that I am loading exactly what is loaded in LR into PC. Why it is required, we shall understand when we study the pipeline architecture. It implies that before I actually return from the exception handler, I need to correct the value stored in LR so that I come back to the correct instruction which is to be executed. And I have told you that all these exceptions have associated with them a vector, that is a memory location. That location is accessed for getting the instruction for the handler. we go into the handler, and when I have completed servicing of the interrupt, I come back from the handler. Before coming back from the handler, I should adjust the LR value. It may also so happen that I might like to store the LR value as well as other registers into the stack, because I would like to retain their values. Then I need to do what before I come back from the handler? Restore the register values and then return from the handler. Next question is interrupt assignment, and this interrupt assignment, this is particularly important when we are looking at the hardware devices and we are assigning interrupts to the hardware devices. In many a times, why should I say many a times, in almost in all universal implementations, you have an interrupt controller with the core CPU. The interrupt controller connects multiple external interrupts to either FIQ or IRQ. In fact, IRQ are normally assigned to general purpose interrupts. In fact, periodic timer interrupt to force a context switch when you have a multiprocessing, okay? When we have concurrent processes running and the CPU has to switch from one process to another process, that switch takes place because of an interrupt from the timer, because timer is programmed to allocate a fixed time slot to the process. Now, these kind of general purpose interrupts, which is for the purpose of maintaining OS, are associated with IRQ. The critical devices which are to be serviced with very less latency, they are associated with FIQ. So, what we say that FIQ is always reserved for an interrupt source which requires fast response time, because it is having minimum interrupt latency. And in fact, the issue is that for an application in an embedded system, the environment, the external signal property decides how much latency you can actually allow for. Okay? In case of this periodic timer, this latency is a more of an OS consideration and not of the property of the external signal. But when we have to handle a very first external signal with less interrupt latency, that becomes a signal coming from some kind of a dedicated peripherals or a dedicated application. So, that interrupt is associated with FIQ. So, obviously, now the question is interrupt latency. So, I had already discussed this point earlier, and I am again coming back to this point because interrupt latency is a very key issue in designing an embedded system. It has got both components, hardware as well as software component. Now, there are software methods to reduce latency. Okay. Hardware is as you have been provided by the architecture, and you have found that FIQ, the example of ARM, that provision of a copy registers becoming available, is a hardware solution for reducing interrupt latency. Even in the software, we can take certain steps. One of the steps is what is called nested interrupts. So, a nested interrupt handler allows further interrupts to occur even when servicing an existing interrupt by re-enabling the interrupts inside the service routine. Okay. And obviously, in this case what will happen? The interrupt which is now raising a request need not wait till servicing of the previous interrupt is completed. And when we are using an interrupt controller, we can associate different priorities with the devices. So, what can happen is that a higher priority interrupt, okay, can actually interrupt a service provider of a lower priority interrupt. Okay. Although so what happens? If I have an IRQ handler, inside IRQ handler, I enable IRQ bit. An interrupt controller is associated with priorities of the external devices. Now, if an external device raises an interrupt and this device has got a higher priority, than of the device whose interrupt is being serviced, my interrupt controller will do what? Will generate another IRQ interrupt request. Since I am using a nested handler, IRQ bit is now cleared. So, that interrupt will occur and I shall now service the interrupt of higher priority device. What is the effect? The average latency of a higher priority device is less compared to that of a low priority device. Now, obviously, for doing all these exception handling, you have understood always that stack organization becomes critical, because for each processor mode, I have got a stack pointer and each processor mode has got a different stack, therefore, okay. So, I need to set up this stack in the beginning itself. So, every time this stack, this is not a single stack. So, what I shall have? I shall have a stack in the memory. So, stack is what? A memory area, and that memory area will be different for different modes. The stack that I am using in user mode is definitely not same as that of the stack area which I might be using in FIQ mode. So, I have to appropriately set the stack pointer values, and that is typically done during the reset mode. Okay. So, change to each mode. So, during reset mode you change to each mode by adjusting the CPSR bit and then writing the correct value onto SP. The other decision is, and this is a design decision of a software developer, that where in memory the stack to be located and what is the mode to be adopted, because I can have all possible modes of stack. Typically descending stack is the most common mode, and the location is defined in such a way that you really do not have a chance to overrun the vector table, and that is very, very important. If you overrun your vector table by stack overrun under an error condition, so you are corrupting the system as a whole. So, you should associate a location with a stack so that you minimize your chance of overrunning the vector table. And in many cases you can actually use a check to find out whether you are overrunning the stack. And the size varies from implementation to implementation, application to application, depending on how you are designing your software. Because if you are really supporting nested interrupts, you will require a larger stack. Say for example, IRQ, in case of nested interrupts, I need to save the registers so that I can come back to the correct point of execution of servicing the lower priority interrupt. Okay, so I shall need the space to save all these registers. So, the stack size requirement for nested interrupt handling is always more than when we are not having nested interrupt handlers. Now, you can realize, since it is an embedded system and it is not a general purpose, I can have an assessment of the kind of external devices and the signals that will generate the interrupts, and what are their latency constraints, and accordingly we can design the interrupt handling scheme and decide on the size of the stack. In fact, IO systems and IO devices are primarily interfaced through this kind of interrupts. So, I have first interrupt and normal interrupt that we had already discussed, and they are used for interrupt driven IO processing. And all IO devices are typically located in the memory map of ARM. So, you have got memory mapped IO. There is no separate IO address space. There is also a support for DMA. So, in fact, these interrupts that we had actually discussed, you can understand and you can realize the basic job of these interrupts to handle this kind of various IO which are external environment dependent. Next, we shall look at these processors and processor cores in more detail. In fact, what we say that ARM CPU core typically consists of the processor core, cache memory and a memory management unit. Now, this memory management unit and cache we shall discuss separately when we discuss the memory organization in an embedded system. Today, our concentration would be on the processor core. We have looked at the data path of ARM7, but not only the data path, there are other obviously the hardware components inside the ARM7 processor. In fact, ARM7 is a low end ARM core which are targeted for applications like mobile phones. Although today things have changed, you get ARM9 and more sophisticated processor being used, but when ARM7 came in, one of the target applications was digital mobile phone. You have got these variants of the ARM core and which are indicated by these letters T, D, M, I. T is basically thumb mode, that means you have got an embedded 16-bit processor inside 32-bit. So, you can switch from ARM to thumb and back. D means you have got a on-chip debug support enabling the processor to halt in response to a debug request. M is an enhanced multiplier which yields full 64-bit result. You may not require it. So, if you do not require it, so you do not have M, that is you have TDI and not TDMI. I is embedded ICE hardware. The architecturally ARM7 is a von Neumann architecture, has got a von Neumann architecture with 3-stage pipelines, and the CPI, the cycles per instructions typically is about 1.9. So, let us look at its organization. So, this is a more abstract level or a gross level organization. What we had looked at earlier, we had looked at the data path which is sitting inside here. So, what we are looking at other than the processor core, there are other components which are there in the CPU core. The fundamentally these are the two blocks, the JTAG tap controller and embedded ICE. In fact, this JTAG tap controller is actually a kind of a port which enables a direct communication with the processor core for the purpose of debugging and running the software. Consider a very simplified situation. You are trying to execute an instruction on this processor core. Now, you know instruction set, so you will be using an assembler, a software development environment. That software development environment will typically run on a PC, okay? And from that PC, I have generated the code and I would like to run the code on your ARM. So, one option is you load it onto a memory and connect that memory area to the processor core. So, when it boots up, that memory area, the initial memory area will contain the instruction and it will start execution from that. The other option is of using this JTAG port, using a JTAG connector. So, if you are using a JTAG connector, what happens is by using the JTAG connector, you can actually inject the instruction onto the processor core, okay. So, this scan chain, this is a set of registers and you can actually inject your instructions into the processor core and what your embedded ICE, this is in-circuit emulator, what this hardware block provides for the support to examine the processor states while this instruction execution takes place. So, what I am trying to say is that these two enables, say just consider this, that somehow this JTAG tap controller enables what? Enables injection of instruction. Instruction is what? Nothing but a binary bit pattern. instruction of that injection of that instruction onto the processor core, and the processor core executes that instruction, and this embedded eyes gives you a provision for checking the processor state, okay, as the instruction execution takes place. Checking the processor state can mean what? Maybe checking the value of the registers. It also enables you to introduce breakpoints. So, what I have enabled therefore by adding these two blocks in the basic core, a communication facility and the ability to see and observe what happens inside when instruction execution takes place. This is the basic bus structure. So, what you have got here? You have got bidirectional data bus. Okay. Here this is the bidirectional data bus, and this is your input data bus, this is your output data bus. These are the two, both the options are available. This is actually your external address bus. This is essentially the control bus. So, this is a very simplified picture of ARM7T DMI organization. In fact, the D and I actually indicator of the fact that I have got this JTAG as well as this embedded eyes sitting in the hardware. It supports, ARM7 supports 3-stage pipeline. So, effectively what you are seeing is that an instruction execution takes place 3 cycles, but since I have a pipeline, effectively what happens? Once the pipeline is loaded, per cycle I can have 1 instruction executed. This is the simplest 3-stage: fetch, decode, execute. At any time slice, therefore 3 different instructions may occupy each of these stages, and when the processor is executing data processing instruction, the latency is 3 cycles and throughput is 1 instruction per cycle. I hope you have understood why latency is 3. And when accessing R15, R15 is address of current instruction plus 8. This is the key point. Why? Because since you are doing prefetching, your PC, when you are currently executing an instruction, your PC gets pointed to the instruction which is currently to be fetched. So, it is PC plus 8, and when interrupt occurs, what happens? The current execution is completed and the interrupt is serviced. If not, is case of an exceptions like data abort or prefetch abort, where actually the exception occurs while execution of the instruction. But in case of FIQ or IRQ, the interrupt is serviced only on completion of the current instruction. Okay. And in this case, PC points to what? PC plus 8. Okay. And these value will get loaded onto LR. Fine. But when you coming back from the service routine, if you start execution from PC plus 8, you are not doing the right thing. You are skipping an instruction. So, LR value has to be correctly adjusted inside the interrupt service handling routine, so that you come back to the correct point for execution. So, there are, but one thing with ARM instruction set is that all instructions are not necessarily single cycle instructions. The typical example is load multiple byte or load multiple or store multiple instructions. So, these are multiple load. So, it has got 2 registers to load, and so the instruction has to be in execution for 2 cycles, and hence execution of prefetched instruction will be now delayed. So, other instructions like branch, subroutine call, exceptions affect pipeline efficiency, and you have already seen that we would like to use conditional instructions rather than branch when you have small set of instructions to execute to have the pipeline working in an efficient fashion. Let us see what happens when an interrupt occurs, okay, in the pipeline case. So, I am executing an instruction. So, I have shown here at this point that FIQ occurs. So, if FIQ occurs at this point, then this instruction will be executed, okay, but next instruction will not be executed. This has already been fetched, and these are the different processing steps which would take place, okay. So, now let us say from here where shall I go? If you look into it, this move instruction, I am just giving you a typical example, say this move instruction, this is what has been fetched, okay, because there is a 3-stage pipeline, and the next is X, because here nothing occurs, because now you are actually decoding IRQ, that is when IRQ or FIQ occurs, and then you are trying to see what is to be done. So, if FIQ occurs, you actually go to 001C, which is actually the vector. Now, at this vector you have got a branch instruction, okay. You are branching to AF00, okay. So, when you are branching to AF00, then this pipeline is again has to be flushed, okay. So, and you are going to this location, and at this location you are starting execution of the first instruction of the interrupt handler. So, effectively what we are seeing here is the minimum FIQ latency has to be here 7 cycles. This is a typical situation. I may do something else as well, but here at this vector, what I have got? At this vector I have got a branch instruction. So, this branch has to be executed to actually move into the interrupt handler, okay. And so, there is a delay of about 7 cycles, and this is how the pipeline would behave. So, once at this point the interrupt occurs, I have to do this is taking place for the adjustments corresponding to the interrupt. So, this has been fetched. So, I go to at this point. When I go to this point, I am actually executing here. This is the branch instruction which gets executed. So, this fetch has already done, and this has to be flushed, and then real execution starts from this point onwards. So, this is actually the first instruction of the interrupt handler, okay. So, this is a scenario where you have got a 7 cycle in FIQ latency. So, this we had already discussed. Now, we are looking at this core, because next what we shall look at? We shall look at the signals which are coming out and going in corresponding to this organization. So, these are the different set of signals. We need not bother about each one of them right now. What is important is to know the groups. You can see that there is a set of signals which are enabling the debug operations. There are a set of signals for external coprocessor interface. These are the power signals. These are for the JTAG controls. JTAG, I told you, is a port through which I can actually inject instructions onto the core. So, I need to have a JTAG control signals. Then you have got the memory management unit interface. You have got this memory interface, that is how exactly the memory is to be connected, external memory is to be connected. These are your interrupt signals, out of which you can recognize that FIQ and IRQ, which are basic interrupt signals. This is a configuration signal which indicates whether it is being configured in a big endian or a small endian form, and these are your weight control, clock control signals. So, this is a kind of a description of the interface signals. What is important and interesting to note, the memory interface. It provides 32-bit address, it has got bidirectional data bus and separate data out and data in. Okay, so, you have got in fact these 3 buses. So, you can have a first data transfer, and there are various signals which indicates a kind of processor cycle which is going on. Now, here we have given a set. So what it tells you is that M request indicates a processor cycle which requires a memory access. It is not that all processor cycle requires memory access. So external devices has to be told that whether a memory request is access is required or not, and also it indicates whether it is a sequential or non-sequential. Okay, that means you are accessing a memory location which will be sequential to that used in a previous cycle or not. Okay. So that enables design of the hardware, appropriate design of the hardware. And the cycles which are defined, you will find non-sequential memory access, sequential memory access, internal cycle. So bus and memory inactive, so these bus now can be used by some other bus controller. Then this is co-processor register transfer. So now the data transfer is to the co-processor register and not to the memory locations. So these are kind of bus status signals which are provided by the ARM7. Then you have got lock. Lock indicates the processor should keep the bus to ensure the atomicity of read and write phase of swap instruction. Okay, a swap means a read as well as write. So I require bus, and bus should not be released in between, because otherwise the data integrity may be at stake. So that is ensured by the lock signal. This read and write, this is a standard read and write indicator, and these signals indicate what is the memory access size. Are you accessing a byte, half word or word? Okay. And this MMU interface, this is a memory management unit. Okay. This memory management unit actually manages the memory, okay, and it takes care of the fact that if it is in a privileged mode, you are if you are in a user mode, you are not accessing a memory area which is allocated to a software which is expected to be executed in a privileged mode. So these memory partitions, virtual memory, all these things are managed by the MMU, and these are the interface signals, because MMU needs to know the mode, because whether it is a privileged or non-privileged mode. It also needs to know how to do the address translation, okay, because if it is a virtual memory, appropriate address translation has to be done. Also it has to indicate the abort signal, that whether this location is disallowed access or not. Okay. Then there is this state which is indicated by the T bit, whether your processor is in thumb state or not, and configuration I already told you. These are all interrupts, and this initialization is a reset signal which forces the processors to start from a known state and executing from this location. The ARM memory interface has got, I had already shown you the cycles, and this is exactly the definition of the cycles, of the details of the cycles. So it says that the ARM code now requires a transfer to or from an address which is either the same or 1 word or 1/2 word greater than the preceding address. This is exactly the meaning of sequential access. This is non-sequential access, where it is not related to the previous address, and this is corresponding to co-processor register transfer. Next we look at ARM9, which is an enhancement over ARM7. Now ARM7 was a von Neumann architecture, this is Harvard architecture. Obviously the Harvard architecture ensures increased data transfer rate, because you have got a separate instruction memory interface and a separate data memory interface. So obviously the memory bandwidth is more. It implements not a 3-stage but 5-stage pipeline, and these changes were implemented to achieve a kind of a CPI of the order 1.5 and to improve the maximum clock frequency. This 5-stage pipeline has got the following stages: fetch, decode, execute, buffer data, write back. In fact, these are the two modes which are, last two are the two modes which are not there originally. Here you can buffer the data or access is the data memory, which is different from instruction memory. And in the organization, we are showing basically the different stages. When you fetch the instruction goes into what is called instruction cache, okay, I cache. So this is where your fetch pipeline stage is executed. Then you do an instruction decode. Here you do the decode as well as you select the registers so that you can actually get the data, enable the operands to come out of the registers. Next is actually your execute stage, where you actually have got your ALU. This is the same barrel register, that shift operation that I talked about. There will be a multiplier block, and these are all operations to do with address manipulations, okay. So pre-indexing and other things, if it is to be done, then this multiplexer comes into the play, this operation takes place and it goes back. After the execution takes place, the results go to data cache, okay, and this is what we call the buffering or the data memory access stage. After following this, you go to register write state, and from here it is actually written back to the registered bank. So these are the 5 stages of pipeline which is implemented in ARM9. And you can realize that we are talking about I cache and D cache. In fact, this is a reflection of the fact that we are talking about the separate instruction memory and separate data memory. And this is a kind of a comparison between ARM7 and ARM9 pipelines. ARM7 had a 3-stage, ARM9 has got a 5-stage. In fact, what we are showing here is that thumb decompress and ARM decode is actually everything put together to a decode, because this is TDMI, that means I have got a thumb mode as well, takes place here. And in this case of a decode, you have got the complete decode here coming into this block, as well as register read is also enabled here. I had already shown that in the block diagram, because I can enable the registers once I have decoded the instruction. Next I do that ALU operation, shift and ALU, which is basically execute. And in fact, in the execute stage, I had the register write as well in ARM7. Now that has been split. I have put in an intermediate data memory access or the buffering stage and a register write stage, because in many cases I shall be writing the data onto the data memory, which is again distinct from my instruction memory. Now 9E is a DSP enhancement. In fact, we had already discussed instruction sets, and architecturally you will find that what is being changed is your ISA, the instruction set architecture. It effectively means that there are enhancements in the ALU of the processor, okay. So you have got a saturation arithmetic, you have got this multiplication and accumulate operations. So let us see other things is, interestingly, there is a CL set, count leading 0 instruction, okay. So if this is required for first-order normalization and division, because if I have a floating point number, if I need to normalize, I need to find out how many leading zeros are there. There is a special hardware block to implement this, because this cannot be done using a standard ALU. And it has got a single cycle multiplier array which speeds up all ARM9E multiply instructions. We shall just look at these enhancement. This is just a part of the data path again of ARM9E. In fact, 9E was obviously when we are talking about multiply and accumulate, and this is an instruction required for primarily convolution operation, and it is an enhancement for DSP application. So what you find is, this is a basic data path enhancement. So you have got this multiplication taking place here, you get a 48-bit or 32-bit product which is added with a 64-bit register or a 64-bit register pair as accumulation source. So these data can be added with the result of this multiplication and stored here. So this is how the data path gets enhanced in case of NE, and this is basically your first multiplier block, because this is doing that multiplication operation, okay, which is built in the hardware itself. So, these are the other combinations of these operands which are possible. This ARM 920T is basically using these as a processor core. This is as a CPU core. This is what you get the complete processor core. So, you have got an instruction cache, instruction MMU, that is, this is the memory management unit for your instruction memory. This is the memory management unit for your data memory. So, you got to have 2 MMUs. In ARM 7 there was only 1 MMU because I was having von Neumann architecture. And this is your external coprocessor interface, and this is AMBA interface. AMBA is an interface protocol for definition of a bus. In fact, AMBA is advanced microcontroller bus architecture, which is ARM's on-chip bus specification. In fact, just like on your PC, if you have got a PCI bus definition, so this is AMBA is a on-chip bus definition. In fact, this is basically your bus structure, and this is your bus interface with the ARM, and these are the other on-chip peripherals which can be connected. So, on the main bus itself, you have got a on-chip RAM, because that will be fast enough. The external bus interface block is also connected to that same bus, and there is a bridge. Through bridge it can be connected to a peripheral bus, because peripheral bus can be possibly a slower bus compared to that of a system bus. So, it is a kind of a hierarchical bus organization. So, on a peripheral bus you have got your timer, you have got your interrupt controller, because interrupt controller will be again interfaced with the devices. And this is your arbiter. If there are multiple bus controllers and they are trying to access the bus, I have to do an arbitration. So, I need a arbiter block. So, this is a very broad overview of AMBA bus. So, a simple ARM based system, what it should be there? On chip there will be an ARM core with a number of system dependent peripherals. Also required will be some form of interrupt controller which receives interrupts from the peripherals and raises IRQ and FIQ input to the ARM as appropriate. So, an interrupt controller may also provide the hardware assistance for prioritizing the interrupts. So, it becomes a part of the hardware. As far as memory is concerned, there is likely to be some narrow off-chip ROM or flash which would be used to boot the system from, because during development phase you will be using the code from the host system maybe to test on the chip using your JTAG port, but actually your code has to go into the flash or a EEPROM for an embedded system. There is also likely to be some 16-bit wide RAM used to store most of the runtime data and perhaps some code copied out of the flash. Then on chip there may well be some 32-bit memory used to store the interrupt handlers. Interrupt handlers are basically the servicing for the interrupts as well as the vector tables and also the stacks. So, typically the picture would be something like this. So, you have an interrupt, this is what goes into the complete thing. You have got an ARM core. You have got the interrupt controller to which the peripherals are connected. Via these peripherals you actually connect the IO devices, okay, and this peripheral generates these signals for the ARM core. This is on chip 32-bit RAM which may have the device handlers, that is your device service routines as well as your stack as well as your vector, and these are the external memories. So, external memory you can use of different kinds. These are 8-bit ROMs or 16-bit RAM, but they have to be organized such that they provide the 32-bit address reference. So, this is a very simple ARM based system. In fact, this is a generic architecture of all ARM based embedded applications, including many of your mobile phones. In fact, Nokia actually use ARM based SoCs in their implementations. Another enhancement of this ARM 5 architecture, since I was talking about mobile phones and we talk about Java enabled mobile phones today in the market. So, you have got an extension which is called J, TEJ, J to support Java virtual machine, okay, for execution of the Java bytecode, because you know Java 1 compilation generates a bytecode which is to be interpreted by the processor. So, that bytecode interpretation requires some hardware features enabling accelerated execution, and that is put in the architecture in the J mode. The other enhancement which has come in with ARM version 6, which is again an enhancement for DSP, target DSP applications, because if it is going for mobile and other applications, you will find that your speech, your camera, your video, these are all signals which are to be processed. So one of the interesting feature is ARM6 is assigned instruction set. This provides high code density and low power. What is assigned instruction set? Single instruction, multiple data. That it uses a single instruction to execute on multiple data, okay? And so it exploits what we call data parallelism. A simple example is this QAdd8. Now what does that mean? See, these registers, these are operands and they will contain their 32-bit registers. 32-bit registers means they will have 4 8-bit data value, okay. So when I am talking about QAdd8, it means I am not talking about a 32-bit addition, I am talking about 4 8-bit addition, and that is why this is an example of SIMD instruction, okay. So corresponding bytes gets added and I use saturation arithmetic. There are other features are sum of absolute difference instruction. Okay, this is again an example of an SIMD. Here I have got 32 bits. So what I shall be doing? I shall be subtracting individual bytes, the corresponding bytes of the registers, and the absolute difference would be summed up. And you can consider that if I am trying to do a compute difference between two small image areas consisting of pixels, okay, what I shall do? I shall subtract the value of the pixels and add it up, and that would give me the difference over a region. So in this case I can use one instruction to compute difference over a set of 4 pixels in the image if you are using 8 bits per pixel. It also got support for cryptographic multiplication, a large multiplication, because many of the coding requires large multiplications. It also has more sophisticated interface for multiprocessing. So what we have got is a variety of features in the ARM core which enables its use for a number of applications. In fact, ARM core or ARM processor architecture has been licensed to a number of users, and they have used Atmel, Cirrus Logic, Intel, Samsung. They are all made products out of it. And ARP is mostly used as a processor core in SoC and SiCs as well. And there are example communication chips built by Philips which has got a GSM add-on to the basic processor. So you will find all such variants coming from a number of manufacturers. And Intel has made one such enhancement which is called X-Scale architecture, which is built around ARM5, okay, TE extension, and this architecture is different. Intel developed its own microarchitecture and coprocessor extensions. So therefore what we have done by now is we have understood the instruction set architecture completely. We have understood the basic organization of processor and the CPU, and we have also understood how the complete exception processing gets handled. So this finishes our discussions on ARM. In the next class, we shall discuss more about other DSP processors which are used in many cases with ARM as a SoC.